This is a video on nuclear reactions. It goes along with pages 15 through 18 in the notes. First question, what do nuclear scientists from England like to eat? Fission chips. Get it? All right, in all nuclear reactions, mass energy is conserved and charge is conserved, and the nucleon number or mass number is conserved. Mass energy being conserved and charge being conserved is true for everything, not just nuclear reactions, but everything in the universe. Nucleon, what is a nucleon? That's the stuff that's in the nucleus. That's protons and neutrons, not electrons. So the amount of protons and neutrons stays the same. We can switch from protons and neutrons between those, but we can't uh, change the total number of neutrons and protons, the total number of nucleons. This is a regions question. During the process of a beta emission, a neutron is converted into a proton, an electron antineutrino, and energy. Um, Based on conservation laws, how does the mass of the neutron compare to the mass of the proton? So the neutron becomes a proton, an electron antineutrino, and energy. It becomes four things. So the neutron has to have more mass because it becomes all those things. And since charge must be conserved, what's the charge of an electron antineutrino? So the neutron is neutral, that's zero. Protons plus one, electrons minus one, so we're at zero. The energy doesn't add any charge, so this has to be zero. So that zero equals zero. Yeah, so it's neutral. 26, when a proton collides with an antiproton, two gamma ray particles are emitted. Would this be considered to be a nuclear reaction? Oops, wrong way. The answer is no. The nucleon number is not conserved. I started with two protons or two nucleons, a proton and an antiproton. That's two. After I'm done, I have zero. I have photons. Photons are not nucleons. Two gamma ray particles are photons. They're not nucleons. The nucleon number is not conserved. That doesn't mean it's not possible. That just means it's not a nuclear reaction. It's a matter-antimatter reaction. Okay, and the nucleon number is not conserved. All right. This is our notation for nuclear physics. We take our element, put it right there. Um, the number of protons goes here, and the number of nucleons, that's protons plus neutrons, goes here. So here we have chlorine, so Cl for chlorine. We have 17 protons, that goes here, and we have 17 plus 18 is 35 nucleons, so it's Cl 1735. Okay, um, a proton is a lowercase p with a one proton and one nucleon, right? Because it's one proton is one nucleon. We can also write it as H for hydrogen, 1, 1. A neutron is lowercase n, 0, 1. It has 0 proton, but it's one nucleon, so it's 0, 1. Electron is just E with a minus. Gamma photon. Photon is no protons, no neutrons. It's nothing. So it's gamma. That sideways fish there is a gamma. It's a Greek letter gamma. So it's gamma 0, 0. An alpha particle. We use a alpha, which is like a sideways fish, or you know, the other one's a vertical fish. This one's a horizontal fish. An alpha particle has two protons and two neutrons. So we have 2 for the proton number and 4 for the nucleon number. It's also, you can also write it as a helium nucleus, He24. It's the same 2 and the same 4. All right, types of nuclear reactions. There's nuclear fission. Fission means things splitting. And fusion means combining things. So we're splitting nuclei and combining nuclei. All right, radioactivity. Radioactivity is the process of nuclear decay, radioactive decay. Nothing new. It's been going on since the universe was created. It warms Earth's interior. It's in the air we breathe. It's present in all rocks, some in trace amounts, and it's 110% natural. No, I'm just kidding. You can't have 110%. It's 100% natural. Okay. Alpha, beta, and gamma radiation. All right, this is where we lose an alpha particle. Alpha particle is a helium nucleus. It's two protons and two neutrons. We just went over this. It's that or that. This is a heavy, short-range particle. It's not able to penetrate human skin or clothing, so it's not very harmful, but it can be harmful if you inhale or swallow it. But it's not going to go through your skin or clothes. Um, right, um, why does alpha decay occur? Some large nuclei like to get rid of nucleons just because some elements are more stable than others. So this is radon and becomes polonium. I'm pretty sure that's polonium. So we start, radon is 86 222. That means it has 86 protons and 222 protons and neutrons. So we shed an alpha particle. So the number of protons is going to go down by 2. So we go from 86 to 84. And the number of nucleons goes down by 4. So we go from 222 to 218. So nucleon, this is a nuclear reaction. Charge is conserved, uh, mass is conserved, mass energy is conserved, and nucleon number is conserved. So yeah, should make sense. The charge is conserved. 86. We had a charge of plus 86 here, charge of plus 86 here. Nucleon number of 222. Total nucleons is 222. Beta decay. A beta particle is an electron. Actually, a beta negative particle is an electron. We can also have a beta positive, which is a positron. This is a light, short-range particle. It's moderately penetrating, so they were named alpha, beta, and gamma because alpha doesn't penetrate much, beta penetrates some, and gamma penetrates the most. Beta particles can be harmful if deposited internally. That doesn't sound good. Um, Wait, we learned about sharing electrons already. Why is this a nuclear reaction? Okay, so this is not just an atom shedding an electron. This is a special type of nuclear reaction. Um, So we have three types of beta decay. Let's look at each of them. The beta minus decay, when the neutron to proton ratio is too large, the nucleus undergoes a beta minus decay. A neutron transforms into a proton, an electron, antineutrino, and energy, and then ejects the electron and the neutrino. Okay, um, so the neutron turns into a proton, and electron antineutrino. Okay, so what's going to happen here is we're losing a neutron and gaining a proton. Okay, so our carbon to nitrogen here, the 6 is going to go up because we're gaining protons, but the 14 stays the same because we lose a proton but gain it, or we lose a neutron but gain a proton. So the total number of protons and neutrons stays the same. Okay, plus our electron, that's our beta particle, plus this is a Greek letter nu for neutrino, get it? It's anti because there's a bar on top, and it's electron with the E. Um, Not that important here, but what's important is that our charge is conserved and our nucleon number is conserved. The nucleon number is 1414. The charge here we're plus 6. After we're plus 7 minus 1, plus 6. Okay, that's our beta minus decay. Okay, beta plus decay, when the neutron to proton ratio is too small, a proton transforms into a neutron, a positron, and an electron antineutrino. So here we have some fluorine. Okay, a proton turns into a neutron. So the number of nucleons is going to stay the same, right? 17 to 17. Proton to neutron, the protons and neutrons stays the same. Number of protons goes down though. We go from 9 to 8, right? Because the proton became a neutron. But that means we have missing this charge here is plus 9. The charge here is plus 8. So we have our extra charge of plus 1 right there for a total of plus 9 on the right side. The neutron and the neutron and the positron. Note, since a neutron has more mass than an electron, this will never happen to an isolated proton because it would violate mass energy conservation. The energy must come from the binding energy in the nucleus. So it has to be energy in the nucleus to make this happen. Okay, but again, The nucleon number stayed the same, 17, 17. The charge stayed the same. We went from 9 to 9. All right, the third and final type of beta decay is called electron capture. It's similar to the beta plus decay, turns a proton into a neutron, but the proton captures an orbiting electron. The proton electron transform into a neutron and emit an electron neutrino. So we have some beryllium here. It captures an electron, so the electron's on the left. Okay, so the proton turns into a neutron. So our proton numbers go down. Okay, we go from 4 to 3, but the nucleon number stays the same. 7 before, 7 after. Okay, is the charge conserved? Of course it is. We have 4 minus 1. We have 3 on the left. We have 3 on the right. So the charge is conserved. All right, there is something I want you guys to know. You don't have to memorize all of these. You just need to understand how to apply um, the nucleon number being conserved, the charge being conserved. You need to be able to show which would be correct and which would be incorrect. I'll give you some questions on that later. But you don't have to memorize all the details of a beta decay. Last type of decay is gamma decay. Gamma's high energy photon. Um, very harmful, not good for you, unless you want to become the Incredible Hulk. Gamma decay occurs in nuclear reactions when the nucleus is left in a high energy excited state. So I know you learned about electrons being in excited state, but the nucleus can be in an excited state too. Typically after alpha beta decay, the nucleus drops to its ground state and emits a high energy photon. So if you notice, nothing's changing here. We have uh, the 20 stays at 20, the 42 stays at 42. The star indicates it's a high energy state, and then it just gives off the energy in the gamma particle. So that's our gamma decay. All right, so you should pause here, answer some of the questions, and when I resume, or when you're ready to resume, we'll go over the answers. Okay, let's go over the answers. Okay, first one, the origins of radioactivity go back to when time began, basically. Indeed, before humans emerged on Earth. Number two, any atom that emits an alpha particle or beta particle um, becomes an atom of a different element always. If we're an alpha particle, we lose 2 protons. And if we're beta decay, we lose or gain a proton. And anytime you change the number of protons, you change your element. So it becomes a different element. Which of these is the nucleus of a helium atom, the alpha particle? Which of these is a high-speed electron? That's the beta particle. When an element rejects an alpha particle, the atomic number reduces by 2, and the nucleon number goes down by 4. Don't forget that. When an element ejects an alpha particle and a beta particle, the atomic number of that, so beta particle, it's going to go up by 1. Alpha particle is going to go down by 2. So combine them, reduces by 1. Atoms can transmute into completely different atoms in nature or laboratories, both. In either a fission event or a fusion event, the quantity that remains unchanged is the number of nucleons. C. Protons can change into neutrons. Neutrons can change into protons. The mass of everything can change because E equals mc squared. We're losing energy, gaining energy, but the number of nucleons stays the same.